Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to evaluate an improper integral of the second kind, which is that you don't have any infinity or minus infinity popping in one of the limits, but the function, the integrand, becomes discontinuous at the interior point of the interval of integration. Okay, so it could also happen at multiple interior points. Okay, so that your function shoots off the infinity, so that's the infinity discontinuity. There is a specific remedy to sort of handle these integrals. Let me just show you what it is. So here are the guidelines for handling improper integrals with infinite discontinuities. So let's say like f has an infinite discontinuity at point b, which is in fact the upper limit of the integration. What you can do here is that you replace that b by c, and you approach c by b from the left. So this way, you reduce an improper integral to a proper integral from a to c f of x dx, and for that one, you can use the fundamental theorem of calculus on all the integration techniques that we learned earlier. And once you have written the final output of that integral, then you pass the limit as c approaches b from the left. Okay, so it's a two-step approach. And in the second bullet item, you can see that there is the infinite discontinuity of the function at the lower limit. And I'm going to apply the same strategy. I'm going to replace a by c. And now I have a proper integral to deal with, integral c to b f of x dx, and use the fundamental theorem of calculus and all the integration techniques. And once you're done with that, pass the limit as c approaches a from the right, because the improper integral results in something involving c, and you're going to sort of like play with that in the limit operation. So what happens if the infinite discontinuity does not happen at the endpoints, but an interior point within the interval of integration? So let's say like c is a point, not a, not b, but c as an interior point. You have the infinite discontinuity. Then what you're going to do is splitting integral into two pieces here. One is from a to c, and the other one is from c to b. So a to c is the very first bullet item where you have the infinite discontinuity at the upper limit. And c to b is the second kind here, second bullet item, right? Then where the lower limit has a problem of discontinuity. Okay, so then you're going to apply the techniques in first and second bullet items to take care of each integration. All right, so this was a very long intro. We have a lot of exercises to go. Why don't we get started and have this ready with you so that I'm going to refer back to these guidelines. All right, let's get. All right, let's start with part A. This is the integral from 0 to e, ln x squared dx. And none of the limits involve infinity, so this is the improper integral of second kind. Let's check, in fact, to just convince ourselves that ln x squared is the function that we're working with. And the interval of integration is 0 and e. Okay. First observation is that ln x squared is not continuous on 0e because ln 0 is negative infinity, so it blows up. So if you have your TI-84 with you, make it ready and try to graph ln x squared starting from 0 all the way to e. So x min could be 0, x max could be e, and please do it right now. You can pause the video, and I want to show you how the graph looks like. Okay, so the blue graph here. The blue graph here is ln x squared, okay, plotted from 0 to e, okay, so 0 to e here, okay, and at 1, obviously, ln 1 is 0, so we hit the x-axis, but going back in this direction here, as you see, the values approach negative infinity. In fact, y-axis is a vertical asymptote. Okay, So we have to sort of like handle this carefully. Plus, there's another observation here that since we're dealing with the integral from 0 to e, so we're adding negative areas. So these are negative areas to positive areas. So I wonder what's going to happen if they're going to if the negative areas are going to cancel the positive areas, even though the negative area is an infinite area. Okay, this is a finite area as you see, and this is an infinite area. Even though this area as you see going down is teeny tiny small, doesn't matter. It's an infinite area. Okay, so let's see what is happening. Let's see what's happening right here. Okay, so what I'm going to do here is to apply one of the strategies we discussed earlier. So essentially, the lower limit is the problem limit. So what I am going to do is to consider this case here. Okay, the second case here. So the lower limit is a problem limit. So I'm going to approach it from the right. So I'm going to replace that by c, and I'm going to approach c. So c is going to approach, in other words, 0 from the right. Okay. So let's go back and use this strategy over there. So this limit is equal to limit c approaching 0 from the right. Okay. 0 plus, right? And the lower limit is going to be c, upper limit is going to be e, and I'm going to try to integrate ln x squared. Okay, that's a totally separate deal. Okay, that's why I am going to reserve some space here to take care of ln x squared dx. Okay, and we're going to use all the skills that we gained earlier for the sake of integrating this. One thing that we can use from pre-calculus is that ln x squared is in fact 2 ln x, right? You can always pull the exponent, right, out. So 2 ln x dx. And we don't have a formula to directly integrate ln x. So because ln x is not one of the elementary functions in the integration table, okay? So what we're going to do is using integration by parts, okay? So 2 is a polynomial, ln x is logarithmic. Remember our Liate business, right? Liate business. And I have logarithmic and algebraic, in other words, polynomial in this context, right? So I am going to call u to be ln x and dv to be 2dx, okay? And apply integration by parts, obviously. For this, I need du. That's 1 over x dx. And v is the antiderivative of 2. That is 2x. Okay? All right, this integral turns out to be, it's right here. Okay, this integral turns out to be uv, so 2x ln x minus v du, which is just 2 dx. Okay? So wrapping everything up takes us to 2x ln x minus 2x plus c. So this is the value of the indefinite integral, but I'm going to use it towards calculating this definite integral here. And then after all, I am going to pass this limit here. Okay? So carrying that forward, let's write down the antiderivative here. And I don't need any c here, okay? So because I'm doing definite integration from c to e, okay? So as c approaches 0 from the right, let's plug in the upper limit. 2e ln e, but ln e is 1, right? So it's just 2e minus 2e, okay? And then let me just maybe close the bracket here and open another one for the lower limit. Okay, 2c ln c minus 2c. Okay, so
Well, 2e and 2e cancels here. So what we have at the end here is this limit as c approaches infinity. Okay, 2c minus 2c ln c. Okay, and I want to handle this limit carefully because c approaches 0 from the right. The very first 2c is fine, but 2c ln c is not a well-behaving term because it's 0 times negative infinity type indeterminate form. So I'm going to clean this blue stuff up, the indefinite integration part. I'm going to continue from there. All right, let's continue from here. I'm going to split this into two different limits. And one is sort of easier to deal with. Okay. In fact, the first one is sort of like easier to deal with because this limit is equal to 0. Okay. And all I need to care about this limit because as c approaches 0, this 2c approaches 0, but ln 0 is already, ln 0 on the right is approaching negative infinity. So it's like almost like 0 times the negative infinity type indeterminate form. So to handle that, if you remember the L'Hopital's rule business, so to be able to use that, I have to convert this to either 0 over 0 or infinity over infinity type indeterminate form. So what I'm going to do here is that I'm going to leave 2 ln c here, and I'm going to write c as like 1 over c. So I'm sort of like doing some manipulation here so that ln 0 takes you to minus infinity and 1 over c takes you to infinity. So this is still infinity over infinity type indeterminate form. Okay. So what we did here is just this form is turned into this infinity over infinity indeterminate form. Okay. But this allows us to take the derivative of the top and the bottom separately by using the L'Hopital's rule. Here we go. The derivative of the top is 1 over c. The derivative of the bottom is negative 1 over c squared. So in turn, so this whole ratio, after you simplify it and by flipping the bottom over, is exactly equal to negative c. Okay. Therefore, as c approaches 0 from the right, negative c approaches 0, this whole limit here tends to 0. So that means this improper integral is convergent. And as well, the value of this integral is equal to 0. Okay. So going back to this graph here and the original question that I asked earlier, so is the negative area, so negative area plus positive area, that takes us to 0. That means this negative area, which is an infinite area, is something finite, so that I was able to cancel that out with the positive area. So even though it looks like that we have an infinite area here, as you see, right? Even though it looks like we have an infinite area here, and that area is the same as the area right here. Okay. All right, and negative area cancels the positive area. That's exactly what the value of the integral is. All right. Woohoo, this was a long question. Please move on to my next video to see what I'm going to do for part B. Bye.